Good morning. What I wanted to look at now is item 5 on your worksheet that I gave you the other day, calculating a positive predictive value. The reason I'm doing that is because it's important for us to be able to do this, given there are some items on the exam, or the quiz, excuse me, that are related to positive predictive value. So we know that, and also with sensitivity, we know that if you read this question, that there's 1,000 children being tested for asthma with a new screening device. We know that the prevalence of asthma is 9.1%. The sensitivity of the new test is 0.75, and the false positive rate is 0.20. Okay, so let's go ahead and set up this problem and complete it. So I'm going to move this out of the way here and get to my bamboo tablet. And we'll get to work here. Okay, so there's a couple things that I said that we already know. We know that sensitivity is 0.75. So if you recall, sensitivity is the probability, and I talked about this, of a positive test result given that you have the disease. So if you think about what that means, what a positive test result means, if we go back to this conditional probability, we know that this means the probability of the intersection between these two events, right? Divided by the probability of the disease. So we know that the probability of the disease is just its prevalence. So if you're given information about the prevalence of a disease, we can figure everything out. Actually, we can take this whole issue here and figure it out in terms of, make it into a contingency table. So you could have disease positive, disease negative. You could have test positive, test negative, right? And also totals. So one thing we know is that we have 1,000 individuals, because that's what we were told, right? With the problem, we have 1,000 individuals, right? And let's see what else we were told. We were told that the prevalence rate here is 9.1%. So we take 9.1%. That's the same. I'm going to pull up my little calculator here. So if we take 9.1%, that's the same as saying 0.091, and we multiply that times 1,000. We have 91 individuals that have the disease. So we can actually write that down in our table here, that we have 91 individuals with the disease, right? We have 91 individuals with the disease. So that's what we know so far. Let's see, what else do we know? We know that our sensitivity is 0.75. That means among people who have the disease, the test was positive 75% of the time. So we can figure this value out as well. This is kind of fun stuff to do, believe it or not. I know you might not think it's fun, but I think it's fun. So we can go multiply 91 by 0.75, right? 0.75. And we get 68, so let's say 68.25. Let's just write that down. 68 people. 68. Let's round that to the nearest whole number. Oops, I had it upside down. That's why it wasn't working. So we got 68 individuals here. All right, so we got 68 out of 91 individuals. So we just have to fill in this value here. So it's 91 minus 68. So 91 minus 68. 23 individuals. So 23 individuals who have the disease tested negative. So we can put 23 in here. Oops. 23. All right, there you go. So we've already figured that out. Now, if 91 individuals have the disease out of 1,000, then we just subtract 91 from 1,000 to get the ones who don't have the disease. So let's go ahead and do that. 1000 minus 91 equals 909. So we can fit 909 in here. So this is This is the way you use the information to complete the contingency table. Okay, so we got 909 individuals don't have the disease. We know that the false positive rate is 20%. So false positive rate. So here we have the positives, their row, and the negatives. So 20% of those who do not have the disease are told that they do have the disease. So we just multiply 0.20 times 909 to fill in that little box. 909 times 0.20 equals 181.8, so let's round it up to 182. So we can fill in this box, this cell here, with 182, and all we have remaining to do is to complete this 1, 2, 3 more cells here. So we can subtract 182 from 909. 909 minus 182 will give us 727. So we put 727 here, right? 727. So if we add 23 to 727, we got 750, right? 750, right? So only we know we need 250 more spots, because 1,000 minus 750 is 250. So get 250 here. And voila, our table is complete. So isn't that nice, right? So we can actually complete this formula here to get our sensitivity of the test. So what's the probability of both having the disease and testing positive, right? That's this intersection here. So that's 68 individuals out of 1,000 individuals both had the disease and tested positive. So we can actually just take that and go 68 divided by 1,000. That will give us 0.068. 0.068, correct? 0.068. So let's write that down here somewhere. 0.068. All right. So there we go. We have our value of sensitivity. I didn't mean sensitivity. I'm sorry. We have the intersection for the top, and now all we have to do to get the sensitivity is divide 0.068 by the probability of the disease, which we know is already 0.091, because 9.1% have the disease. And that'll give us, let's just do that, 0.068 divided by 0.091, and that equals 75, right? 0.747, which is 75%. 0.75. Now, if I pull back your assignment here, you'll notice that it says the sensitivity of the test is 0.75. So we've replicated what we have. The reason I showed you how to do this is because you actually may have a problem in your quiz related to this issue of calculating a sensitivity. So now you know how to calculate a sensitivity. Isn't that fun? Yeah, I think that's really fun. Okay, so let's go ahead and do that last problem. We want to know what the positive predictive value of the test is. So let's go ahead here and do this. You could say PV for predictive value rather than positive predictive value. We know that this positive predictive value is the probability that one has the disease given that one tested positive, right? And that's the same as here the probability of the intersection between having the disease, having the disease and testing positive. That's an inverted U. I know it looks ugly, apologize. Divided by the probability of testing positive, right? Okay. And what this equals here is, okay, so we need to get this intersection, and we know from the multiplication rule that this is the probability of, well, we're already doing the probability of D given T, so let's do the probability of T given D, right? So probability of test plus given that one has the disease, and we know that this is actually the sensitivity times the probability of having the disease. We divide this whole puppy here by probability of T plus given D plus times probability of, times the probability of D plus. Okay. And then we add to that, let's see if I can make this a little smaller since I'm leaving myself too little space here. The probability, so if you remember, this is on the bottom we have the rule of total probability, right? So in this case we're looking at where the intersection of having the testing positive for the disease and having the disease versus testing positive for the disease and not having the disease. So we talked about that before when we did the example of the total probability in class. So here would be the probability of a false positive result. So D minus, sounds like a bad grade, times probability of D minus. Okay? Alright, so that's what we have here. So again, this on the top here, this part is sensitivity, this is prevalence. So again, we have sensitivity. Sensitivity is a positive test. When one does have the disease, probability of the disease is just prevalence. And then here we have false positive because one is tests positive but doesn't have the disease, times the probability of not having the disease. Okay? So let's go ahead and fill this out with the information that we have. Alright. So we already know that, so let's go back here and go probability of the disease given one test positive. So that's a positive predictive validity, or PV, predictive validity, whichever one you want to call it. We know that at the top, we just showed what we need. We need the sensitivity of the test. The sensitivity of the test, right? And we know that it's 0.75, and we multiply that times the prevalence of the test, which we know is 0.091, okay? And we divide that by the same value, 0.75 times 0.091, right? Okay, and then we add to that the false positive rate, which was 0.20, and we multiply that by 1 minus the prevalence. So if the prevalence is 0.091, well, we know prevalence is the same as having the disease. So having the disease and not having the disease are mutually exclusive events. So then if one has the disease, not having the disease would be 1 minus the probability of having the disease. So it's 1 minus 0.091, which would equal 0.909. So this would be 0.909, 0.909. So we know that because we know that the sample space equals 1, right? So if there's only two possibilities, either you don't, if the sample space is composed of two possibilities, having the disease versus not having disease, and nothing else, the probability of not having the disease plus the probability of having the disease must total 1, okay? They must total 1. So this is what we get, and if we were to go ahead and work this out, let's work this out here. So clear, so 0.75 times 0.091 equals 0.06825. So this is going to be 0.06825. And And we'll repeat that in the denominator, 0.06825. I'm repeating that because that's this right here is the same as this, right? Okay? And we add to that 0.20 times 0.909, 0.20 times 0.909 is 0.1818. So it's 0.1818 here. And we go ahead and add this up. We get 0.06825 divided by this sum, which is 0.2505, 0.2505, right? And we do that division, and we get 0.27. So the positive predictive validity of the test, or the predictive validity of the test, is 0.27. 0.27, or 27%. Okay. All right. So that just tells you that when one is positive for the test, 27% of the time they actually have the disease, which doesn't sound very good, but again, that has a lot to do with the prevalence of the disease. Okay. So this should help you out in calculating your problems.
Time to work on my next evil plan.